Hello, guys. How are you doing?
Good.
How was your weekend?
Fun.
Fun, good. What did you do?
Not differential equations.
I know. It looks on your face. I know. I understand you finished your exam on Friday, so yeah, not differential equation. It was for fun. I agree with you. Right, Queen Heart? Queen Heart.
Here, sir, can you hear me?
Yes, I can hear you now.
Okay, good.
So Rodriguez is here, Ismail Taylor is here, Nathan Light is here, Queen Hart is here, Paul Mustaine is here, Solomon Harris, Nick Campbell, Margie, Will Hostetter, hi, and Gage Levine, Elias Tyson, and Alex is here too. So all
Hello, sir.
sounds good. Alex, how are you?
I'm good, sir. Did you get my test?
I did.
All right.
Did I think I graded your test. You didn't.
I looked. I didn't see a grade for it. I saw a grade for the homework.
Are you sure?
Yes.
Then I think you're not submitted. I couldn't open you. I think I put some remark, right?
Yeah. And
Yeah.
I went and checked it, and I could open it. I can
You
try to
open
read
it? Then why not me? I'll double check. I tried 3 times, and that's why I put. I sent the email to you. But anyway, I'll again.
All right.
Okay, guys. I think you guys are happy with your grades, right? Except one. You guys did a wonderful job. Wonderful job, all of you. Good. I like it. Just keep it up, guys. Almost all you guys are doing really good job. So please keep it up. Please keep it up. Keep it up. Only 12 days more to go and we are done. 12 more days to go and we are done. Will you please let me know what is our final exam, when our final exam is, the time?
June 19th.
June 19th, and I think it is 8 a.m. or 8:30. Let me know time.
I don't know.
June 19th is Friday, right?
Yes, sir. It's Friday.
Yeah.
Please check.
Yeah,
Please
it
check
is.
your canvas. Please check your canvas. Any one of you, please, and let me know, please. I
Friday
think it is
is the 19th. Next Friday.
no next Friday, but what's the date? I mean, it's a time.
Next Friday is the 19th.
Time. Exam time.
Oh, the time. I thought you said
Time.
I'm looking at Canvas.
Please. And guys, I have one more request for you. So many times how I've been telling you to look at the videos. How many of you have gone through my videos on YouTube? Please subscribe to my channel and click on bell icon so you will be notified when I upload the next video, right? If you subscribe that one and if you click on the bell icon, whenever I put new video, you will be notified these things. So you don't have to wait for that. Immediately you will come to know about the uploadings. So yeah, if it is possible, do that thing. Yeah, I put, I think almost all the videos, and probably that would be really helpful to you before your final. So I just request you try to go over the things. If you have some doubts, some problems, just try to go over the things. And hopefully you can solve all your doubts just looking at the videos. Otherwise, you can talk to me and we can discuss that thing too. Please guys, don't forget to subscribe that channel and click on the bell icon. Okay, so time is, what is the timing? 8:30 a.m.?
I think so. I'll check to make sure.
Yeah,
And
please
sorry,
check.
I just checked my test 3. For me to resubmit it, it's locked right now. You'd have to reopen it, or do you want me to email it to you?
Just email it to me.
All right.
Okay.
Sir, I noticed something. When I was on Canvas, the test 4 practice test is in here as like a code, not a document.
Code.
So,
Practice test 4.
yeah.
No, just check Canvas, go to the file section and look at here. Look at here.
It's
Let
showing
me
up
say,
as like a
let me
computer.
share my screen. See, in this one, this is the practice test. If it is not there, please let me know. I cannot.
Ours doesn't look like that, sir.
Yeah, ours looks
Right.
like this, and it's like a just computer code all the way through.
Mm-hmm. I hope
So
you are getting this one. Yes or no?
No, sir.
No. Okay, I will make sure. I will make sure to upload this. This is the practices. Look at here. Example number 1, 2, 3, 4, 5, 7. And the back side is 8, 9, 10, 11, 12, 13. Out of this one, question number 1, 2, 3, 4, 5, 6. They are from chapter number 5, applications of second and higher order differential equations, mainly second order, spring mass system, electrical network. Question number 7, 8, 9. Oops. Question number 7, 8, 9, 10. 7, 8, and 9. These three examples, they are based on Article 8.1. That is simultaneous linear equations. Sorry. Yeah. And roots are real and distinct. Example here, 10b. That's the most important example. And in which roots are real and same. And finally, example 11, 12, and 13, they are based on Laplace transform. We are done. So today is 8th of June, and today is Monday. So we have these 5 days. In these 5 days, I would like to cover at least your chapter 7. Just wait, guys. Hello.
Yes, sir.
Hello. So chapter 7, and then after, sorry, chapter 5, and then after some of the portion of chapter 8, maybe chapter 8 completely. And in the beginning of the next week, I would like to go over chapter number 7. So this week work is chapter 5, application or spring mass system, I would say, and chapter 8, simultaneous linear equations. And then after next week, Monday, I'm going to start Laplace transform. It will take 2 days for me to finish Laplace transform. And then after, you have to take your exam, last test, number 4, on next Wednesday, following Wednesday. Then after, because if you take your exam on Wednesday, I can return your exam. I will try my best to return your exam on Thursday, so that if you want to look at your exam, whatever you did wrong like this, probably it will be helpful to you for your final, because you're taking your exam final on Friday. So Thursday, I would like to return your exam. And if you have some doubts, we can solve that doubts. We can go over a few of the things. If you have some questions for me throughout the syllabus, and Friday will be the exam time. Sounds good, guys? So that's the plan. I told you very first day that it's a very lengthy course. If you look at the book of Zeal, Elementary Differential Equations, if you look at that book, we are almost finishing the book except 2 or 3 chapters. Yeah, just in one semester, we are finishing the whole book, and it's a nice book too. I told you so many times, nice book.
Sir, the exam is on June 19th, 8 a.m.
8 a.m. or 8:30? Oh my God.
8 a.m. That's what it says on the catalog.
Okay, usually it is 8:30, but that's fine. 8 a.m. Thank you so much for letting me know this thing. I will be exactly online, because see, for the final, for internals, it's in our hand, but final, we have to follow the owner codes via my owner code. That means 8 a.m. That means we have to start exactly at 8, and we have to finish exactly at 11. Yes, guys, I can't give you, if I want to, even though I can't give you more time. So please be careful. And I will be online before 8, maybe 7:45. Yes. If you have some last minute question or like this, but exactly 8, and I'm going to post everything, Canvas will be open exactly at 7:55, and you can start your exam at 8. So make sure that all your technologies, your internet, everything is working smoothly. I would appreciate if you can start preparing yourself at 7:30. Yep. I'm talking about June 19th, Friday, early morning, 7:30. Make sure that you have everything, because I will not allow you to leave your chair, leave your room without my permission at the exam time during 3 hours. So make sure you have everything. water bottle, your stimulator, everything that's with you, right? We will discuss this thing. Right now, I would like to focus on chapter number 5. Last time we started, now one more thing. This is the formula set for chapter number 8. First one, that is for article 8.1, you can see where eigenvalues are real and distinct, and here eigenvalues, because whenever your system of equations at that time, we don't have any other choice except matrices, right? Except matrices. Yeah, so that's the thing. And whenever eigenvalues are real and same, in that case, we have to follow this one. If you look at this formula, probably you will not get anything right now. But when the time will come, I will let you know how to use this formula to set up your roots, set up your answer for real and same eigenvalues. So that's what we are going to do in last 2 weeks, I would say. I give you the complete plan, and see, every day we are meeting, we are doing so many things, even though we will be we will be continuing up to the last day. So I told you it's a lengthy syllabus. Anyway, guys, that's fine. That's fine. That's not a big deal for us. This is the practice test, or you can say packet. And I want you guys to keep this packet open in your canvas. Do you have this one on your canvas? I'm not sure. If it is, I think it is there. Just keep this packet open, because I will be asking you to read the example.
Sir, we have a 3-page .tex file on Canvas. It's not a PDF, and it's not 84 pages, that's for sure.
Okay. We will do that thing. Just wait.
Okay.
I will do this thing after the class probably. So right now, you know, the last time we went over the first example of mass weighing. Let me make it larger. Yep. Yeah, a mass weighing 2 pounds stretches a spring 6 inches. At t equal to 0, mass is released from a 0.8 inches below the equilibrium position with an upward velocity 4 feet per second. Determine the position equation of motion. And I told you that here you are given 6 inches, here it is feet, so you have to convert everything in terms of either inches or feet. Feet is more comfort. I'm comfortable with the feet, so that's why I just would like to convert this one in terms of feet. So I converted this one in terms of feet. I converted this one in terms of what? Yeah, this 8 inches in terms of feet. 8 multiplied by 112, right? Or 8 divided by 12. Here is 6 divided by 12. And then after this, so I use the standard equation that m into d square x by dt square plus k x equal to 0. There is no damping force over here in this equation, in this problem. So I am using that equation. This gives me the initial condition, right? Whenever it is moving towards the gravitational force, we are using the plus sign. If it is in the opposite of the gravitational force, upward velocity, that means we are using the negative sign. Sorry. So that's how we solve this problem. The second problem, that was what? A mass weighing 4 pounds is attached to a spring whose spring constant is given to you, right? So we are not finding spring constant over here, that W equal to mg, and then after the spring constant, right? We are not finding that one over here because it is readily given to us. So we can just plug the values of this one. And what is the period of the simple harmonic motion? I told you that frequency is nothing but 1 over reciprocal of the period, and period t is given by 2 pi over omega, right? Angular velocity. So if you find this one, just plug the values and then you can get the answer. That's what we did for the second example. Third example was also almost similar. So we solved third example also last time. Third example is a 20 kg mass is attached to a spring. If the frequency is same thing, the frequency is given to you this time. So what is the spring constant? And we are looking for the spring constant, right? So F equal to Ks, and you are looking for F is given to you 20, and K you are looking for, and the frequency is given to you. So with the help of frequency, you can find the period. Using period, you can find your W, yeah, right? T equal to 2 pi over W. So just use that formula. And then after you can find the spring constant, and then after change your F to 80 kg, that is the second one. So that's what we did last time, right guys, last Thursday. It's been a long time, and that's why I repeated all these three things. And now we are going to start the next part of our example or our syllabus, that is article 5.1.2. Article 5.1.1 is over, that is the spring mass system without damping force, free oscillations, you can say free damping. Okay. Article 4, I mean to say example number 4, if you read this one, a mass weighing 24 pounds attached to the end of a spring, stretching it 4 inches, right? So one end is attached to the spring, and other end, the mass weighing 4 pounds is hanged, and it stretches the spring 4 inches. So 4 inches stretching is there. Initially, the mass is released from the rest from a point 3 inches above the equilibrium position. 3 inches means, again, I have to convert everything in terms of feet. 4 inches in terms of feet, so 4 divided by 12, 3 divided by 12. 3 inches above the equilibrium position means up, that means the negative sign. And then find the equation of motion, right? So here also we don't have any damping force. So I think this fourth example is exactly similar to your first example. I think we covered this part too, right? We discussed this thing too, yes, last time. So let me give you this just one example in homework. We discussed example number 1, 2, and 3. I gave you the solution on Thursday. Today, on Monday, let me give you this example as a homework, and let's go for the next one, that is article 5.1.2. 5.1.2. Spring mass system, free damped motion. Now free damped motion. Over damping situation, critical damping situation, and damping and under damping situation. That means previously in 5.1.1 there was no damping force. Now we have a damping force. We have to decide which type of damping force is provided to you. Either it is over damping, critical damping, or under damping. I will let you know what we mean by all these three different dampings, right? Good. First of all, I think it is better if I can explain to you this thing using the example. A mass weighing 8 pounds stretches a spring 2 feet, right? Stretches a spring 2 feet, mass weighing 8 pounds. So I can start like this: W equal to mg, means m equal to W over g. So W is equal to 8 pounds, 8 over 32. So that means it is 1/4 of slug. That is my m. Am I right, guys? That is my m. Stretches the spring 2 feet, right? So stretching is 2 feet. So F equal to Ks, Kx, right? So you can find the stretching is 2 feet. So X is 2. So you can find Kf equal to 8. So 8 divided by 2, that is equal to 4. So your spring constant, assuming that a damping force numerically equal to 2 times the instantaneous velocity. This line is very important, guys. Assume that a damping force is given to you. Damping force numerically equal to, damping force is usually given by dx by beta times dx by dt. So damping force is numerically equal to 2 times the instantaneous velocity. Now, if I write like this, look at here, please. As I told you, damping is given by beta dx dt, and that damping force is 2 times the instantaneous velocity, means that again it is dx by dt. That means, look at over here, you are going to get something like this. You are going to get something like this. Can you see me on my finger? Yes or no?
Can you move it a little bit to your left?
Just wait. Let me look at my face. Okay, so yeah, this one. So beta dx dt equal to 2 times dx dt. So naturally you can cancel this dx dt. That means beta equal to 2. So this implies that my beta is equal to 2. Right? So my damping force given to us here, that is equal to 2. Previously, my equation was like this. If you remember, my equation was d square x by dt square m times plus kx equal to 0. That was without damping. That was without damping. Whenever damping force is there in your equation at that time, you are not going to use this equation, but you are going to add the damping term in the same equation. That is beta dx by dt plus kx equal to 0. So now your equation will be the second one. Look at here. If you want, you can write it down. This is the second one with damping force. So m into d square x by dt square plus beta dx by dt plus kx equal to 0. K is a spring constant, beta is a damping force, m is the mass. Does it make sense? Does it make sense?
Yes, sir.
Good.
Yes, sir.
Ismail Taylor, where are you? Ismail Taylor, where are you?
I'm right here, sir.
Yeah, don't talk with somebody else. Please pay attention here. Okay? Say him
Yes, sir.
to disturb you after 2 hours. Okay? I have one problem with you. You are doing good in my one course, but you are not doing well in my second course. What's the problem, Ismail Taylor? You are on the track in one of the courses, but in the second one, no, you are not doing well. Justify yourself.
I guess I started slow or something.
Anyway, work hard, and if you need my help, let me know, okay?
Yes, sir.
I told you on very first day that you are a brave guy, so I appreciate your spirit. So please work hard, and if you need my help, let me know. Anyway, so that's a damping force. So I'm going to write like this. So m equal to, my equation will look like this one. I think it is better now. Let me just write it down over here. So it says that mass weighing 8 pounds. So 8 pounds. So W is equal to mg. So m equal to W over g. So 8 over 32, and that is equal to 1/4 of slug. 1/4 of slug. My beta is equal to 2, and stretch is the spring. F equal to kx, F equal to 8, that is equal to k, and x equal to 2 feet. So k equal to naturally 4 lb per feet, right? So I am over here right now. Just look at this one, please. And now I'm going to plug all these values in my equation. So plug these values in the equation. You are going to get 1/4 of d square x by dt square, beta equal to 2 dx by dt plus k equal to 4x equal to 0. If you multiply both throughout by 4, you are going to get dx by dt plus 16x equal to 0. You are going to get something like this. Look at here, guys. Agree? You are going to get something like this. And the ball is now in your court, because now you can find the auxiliary equation. M square plus 8m plus 16 equal to 0. So m plus 4 whole square equal to 0. So m equal to -4 and -4. Equal to -4 and -4. Roots are real and distinct. Roots are real and distinct. Because my right hand side is 0, that means my complementary function itself will work as a general solution. So I can write my xt or xc of t, that is equal to c1 e to the power -4x plus c2 t e to the power -4x. Make sure you are writing t, not x, because t is your independent variable. Okay, so it says what is asked to you. Determine the equation of the motion if the mass is initially released from the equilibrium position with an upward velocity. See, you are not given the displacement. You are just given the upward velocity. That means my initial conditions are x at 0 equal to 0 and x at mass is initially released from the equilibrium position with an upward velocity. So x at 0, mass is initially released from the equilibrium position with an upward velocity. So negative of what? 3 feet per second, right? So negative 3 feet per second. So that is x0 equal to 0, and this is the initial condition. Because the displacement is not given, you can assume that is equal to 0. That is equal to 0. And I think we are almost done, because now you know how to solve this one. So let me start with this solution now. Okay, guys. So example number 1, 2, 3, I solved. Example number 4, I gave you in homework, but I told you I already solved that example over here. Just try to convince yourself. If you are not satisfied, then just try to look at this one, this solution, if you are not satisfied by your work. Otherwise, solve it yourself, because that's the homework problem. And then after spring mass system, free damping motion. Now, let me stop over here. This is half of the example, but let me stop here, because now I want to make sure about my damping. So how to make sure about the damping, that let me first explain to you, and then after we will proceed further with this example. Look at here. Whenever you have m d square x by dt square plus beta damping force plus kx equal to 0, usually we divide by m, and that's what I did in this example, half of the examples. This beta by m, that is actually my 2 lambda. That is my 2 lambda. And k over omega, at k over m, that is my omega square. You know this thing, spring mass system. I used omega equal to square root of k by m, right? I used that formula. So still the same formula is there, omega square equal to k by m. So let me plug these values over here. Let me write this one as 2 lambda, and this is as omega square x. That means this is again a quadratic equation. Quadratic equation, that means I can use the quadratic formula to get the solution. The formula is like this. First of all, the auxiliary equation, you can write m, I don't mind, but already I used m over here. Look at here, 1 m is here, right? Mass is there, and that's why I don't want to write m here. So let me write just p square or some p. So p square, auxiliary equation, p square plus 2 lambda p plus omega square equal to 0. No x, because auxiliary equation is there. So p is nothing but negative b plus or minus b square minus over 2ab. B square minus 4ac divided by 2ab. Now, depending on your nature of your quadratic solution, if this is negative lambda plus or minus square root of lambda square minus omega square, because if you can take this 4 out, because of square root sign 2 out, 2 will get cancelled out. So it is negative lambda plus or minus lambda square minus 4 omega square. Everything depends on this square root sign. If your lambda square minus omega square under the square root sign is greater than 0, that means it is over damping. And over damping means you can see your damping, your graph will be above x-axis like this. If it is equal to 0, means if you are getting only this part is 0, lambda square minus omega square is 0. In that case, it is called a critical damping. You can see the graph will be like this. It's a critical damping. It's almost same thing along x-axis. And if your, my bad, sorry. And if your lambda square minus omega square is less than 0, that is called under damping. You can see the graph moves like this below x-axis and goes like this. Nothing above x-axis. Here it is above x-axis over damping, below x-axis under damping. You have to mention your damping like this. Once you are getting lambda square, once you get this equation, then after you have to compare this equation with your 2 lambda and omega square. Right now, I am over here. Look at over here. My equation is like this. Just try to look at my finger. Try to look at my finger. This one. So d square x by dt square plus 8 times dx by dt plus 16x equal to 0. That means if I compare this one with my 2 lambda, so 2 lambda here, so this is my 8 is equal to 2 lambda and omega square is 4. So 2 lambda equal to 8 and omega square is 4. I am looking for lambda square minus omega square. You don't have to use the square root sign, because actually lambda square, it is now 2 lambda is equal to 8, right? So lambda equal to 4. So lambda square is 16. Omega square is What is my omega square? Omega square is 16. Agree? Omega square is 16. That means I'm getting 0. Am I right, guys? Look at here. Can you see this one? Can you see this one?
Yes, sir.
Yes, sir.
Right? And because of this one, now I have to draw some picture, some rough picture like this. Like this. And that's why I have to mention critical damping. Let's look at here. Critical damping. Critical damping. You have to perform your work like this to claim full points. Right? You have to perform your work like this. If you think that no, you are getting right answer without mentioning damping, no damping force is there, that means please follow my instruction. You have to go through whatever I explained to you. Now let me again go back to my example, and that's what I've been doing. What? Okay, so okay, look at over here, guys. So everything is given to us. Hooke's law, 4 feet lb per feet. I did the same thing. X dash 0 equal to -3. X dash 0, sorry. X dash. Because velocity is then -3 feet per second square because it is upward. I explained this one. It is 8. Here it is 16. Auxiliary equation is this one. Roots are -4 for real and repeated. That's why we are getting this one, right? That's why we are getting. Let me keep this one. Oops. Okay, here. So because of that one, we are getting this one. And here, I just went back to this equation of motion. I compared this one with 2 lambda. So 2 lambda is 8. So lambda equal to 4. Omega square is 16. Right? So lambda square minus omega square is 0. Critical damping. Right? Critical damping, you don't have to mention this thing. This is just for your convenience. Whatever I went over in the previous page, the theoretical portion. Good. And then after use your initial condition that x at 0 equal to 0, that will provide you the first constant C1. Second initial condition, that is in terms of the velocity derivative. Take the derivative of your solution after plugging 0 over here. So my last equation is this one. I want to go for the derivative, x dash t equal to this one. Since my second condition, initial velocity condition is upward velocity is 3 feet per second. So replace this one, x dash at 0, t equal to 0 is -3. And you are going to get second solution C2, plug it back, my bad. Plug it back and you're going to get your final answer. This is your final answer. Any doubt? Let me give you 2 minutes to go over this example. Just look at this one. The example is there in your mind. I mentioned the number, question number 5, example number 5. I don't know what's but look at over here. I give you 2 minutes. Please try to go through this one and then after I will start the next one. Okay, guys. So I hope you don't have any question, right? Shall we go for the next one?
Yes, sir.
Okay. Okay, guys. Read the example. Who wants to read this one? Who wants to read this one? Any one of you, please.
I'll do it,
I'll read
sir.
it.
Yeah, go ahead.
A mass weighing 16 pounds is attached to a 5-foot-long spring. At equilibrium, the spring measures 8.2 feet. If the mass is initially released from rest at a point 2 feet above the equilibrium position, find the displacement x sub t if it is further known that the surrounding medium offers a resistance numerically equal the instantaneous velocity.
Thank you. Look at here. A mass weighing 16 pounds is attached to a 5-foot-long spring. Right? 5-foot-long spring. Mass weighing 16 pounds is given to you. At equilibrium, the spring measures 8.2 feet. At equilibrium, spring measures 8.2 feet. That means you can find your x. See here, the length of the spring, small l, is given to you 5 foot. Equilibrium position is 8.2. Means what is your x? 8.2 minus 5. That means 3.2. Am I right? Do you remember? Please try to recall those three figures I did on last Thursday. One end of the spring is hanged, second one is free. Then after I put some mass and then equilibrium position. The third one is I apply some force. Are you getting me, guys?
Yes, sir.
Yes, sir.
Right? So X is nothing but the stretching in the spring after hanging some weight on the free end. So 8.2 minus 5, that is equal to 3.2. If the mass is initially released from a rest at the point 2 feet above, 2 feet above means negative 2. Mass is initially released, means x at 0 equal to negative 2 feet above the equilibrium position. Initial condition is given to you in terms of displacement. Look at over here, negative 10. It is above means negative 2. Find the displacement xt if the further known that the equilibrium. Now velocity is not given in this example, means x dash at 0 equal to 0. If it is not given, assume it 0. If it is further known that the surrounding medium offers a resistance, this is a damping force. Numerical resistance, that's a damping force. Numerically equal to the instantaneous. Now m times dx by dt, or sorry, beta times dx by dt equal to, numerically equal to, means just 1 times instantaneous velocity is dx by dt, means beta equal to 1. Are you getting me, guys? Are you
Yes, sir.
or not? So beta equal to 1 over here. So now if you go through, the solution, look at here. Oh, 6.1 is just the homework. It's simple, right? Because it's almost same as the previous one. That's fine. Otherwise, you can go through this one. That's not a big deal. See here, as I explained to you, so my x equal to 8/2 minus 5, that is equal to 3.2 feet. 8.2 minus 5 is equal to 3.2 feet. Mass weighing 16 pound means W is equal to mg, m equal to W over g, W equal to 16 divided by 32, so 1/2 slug. Okay, 1/2 slug. By Hooke's law, F is equal to K times X, X equal to 3.2, F is 16, 16 divided by 3.2, so it is, yes please, 1/10/2, something like this, so probably 5, right? 16 divided by 3.2, right guys? So it is 10/2 and that is equal to 5. So 5 lb per feet. That is my spring constant. Plug these values, instantaneous beta equal to 1. Plug these values in your equation of motion, m d square x by dt square plus beta dx by dt plus kx equal to 0. Plug these values, solve that equation. Here your 2 lambda is nothing but, yes, m equal to, just multiply this one. You have to have your coefficient of d square x by dt square highest degree coefficient 1. And then after you can compare find your 2 lambda, find your omega square. First find lambda square minus omega square. If it is equal to 0, critical damping, less than 0, under damping, greater than 0, over damping, right? And then after you can go for the solution of this one and use 2 initial conditions to get the values of 2 constants. You are done. So I explained to you the complete example number 6. Let's go for one more example. Do you have any doubt in example 6? I would say just try it. If you are not getting, let me know tomorrow. I will solve for you. Sounds good? Margie?
Yes, sir.
Yeah, that sounds good.
Nina?
Yes, sir. Sounds good.
Good. All other guys, boys?
Sounds good, sir.
Thank you.
Sounds good
to me.
No, thank you so much. Let's go for example number 7. This same example, only thing is I asked you little bit more things. 2 more parts are here. I want somebody to read this example. I want these 2 guys to read this example. Nina, one is you and second one is who? Boys? Anyone?
I'll do it, sir.
Okay, so Nina, start it. Slowly.
A mass weighing 4 pounds is attached to a spring whose constant is 2 pounds per foot.
Wait.
Offers a
Wait, Nina, wait. A mass weighing 4 pounds. W equal to mg. W is 4 pound is given to you. 4 divided by 32, 1 by 4 slug. M equal to 1 by 4 slug. Agree? Agree?
Yes,
Then
sir.
same sentence says that the spring constant means K is given to you. Why are we using Hooke's law? Just to figure it out our spring constant. But here spring constant is ready-madely provided to us. We are not going to use Hooke's law because spring constant is there, right? The purpose of using Hooke's law to find spring constant, but here spring constant, that's us. So just accept this one. So spring constant K equal to 2 lb per feet. Nina, go ahead.
The medium offers a damping force that is numerically equal to the instantaneous velocity.
Wait, Nina, what is my beta here in this sentence? Nina, I'm asking you, what is my beta?
I'm unsure, sir.
You're not sure? Are you sure?
Yes, sir.
Any one of you? Any one of you?
Sir, wouldn't it be 2, maybe?
It is 2. Why 2? It says it's equal. See, it's equal. Oh, look at the word. It's not 2. The medium offers a damping force. Damping force means beta times dx by dt. So many times I told you. Let me write it down one more time. Beta dx by dt. That means it's a damping force. Look at the last part. Beta dx dt. And it says that is equal to, so let me write equality. Equal to the instantaneous velocity means dx by dt. Equal to means, let me write 1. Let me write 1 here. If you look at this one, now let me know, Nina, what is my beta?
Is it 1, sir, or is it
1. It is 1, right? If you cancel dx dt both sides, beta is 1. You got it, right? So my beta is 1. Go ahead, Nina.
The mass is initially released from a point 1 foot above the equilibrium position with a down.
Wait. Ilyas, a mass is initially released from a point 1 foot above the equilibrium position. How should my initial condition look like? What should be my initial condition? Alex?
Should it be -1, sir, since it's
It is
above the
-1,
equilibrium?
but
Okay.
you need to speak like this. X at 0 equal to -1 feet.
Yes, sir.
-1 foot. Am I right?
Yes, sir.
Right? Please be precise. Nina, go ahead.
With a downward velocity of 8 feet per second.
Good. Ilyas again. What is now second initial condition? Downward velocity is 8 feet per second. X
I'm not
dash
sure,
at-
sir.
Why not? X dash at 0, because it is velocity, means derivative. X dash at 0 equal to plus or minus 8 feet per second downward, means it is positive 8 feet per second. Agree?
Yes, sir.
You got it or not, Ilyas?
Yes, sir. I've got it.
Nina? Ismail?
Yes, sir.
Yes, sir.
Okay. Got it. So go ahead, guys. So go ahead, Nina.
Determine the time at which the mass passes through the equilibrium position.
Wait. Determine the time. Question is slightly different. At which time, because once you have put some weight like this, that means the spring will be in motion like this, upward and downward direction. After some time, it will come to the equilibrium position. Right? So what is the time? At which time, once you start your process, which time the spring will be at the equilibrium position? That's what we are looking for. Means we are looking for time t, small t. Go ahead.
Find the time at which the mass attains its extreme displacement from the equilibrium position.
Wait. Find the time. My second question. Find the time at which the mass attains the extreme displacement. Displacement means extreme displacement means it goes like this, topmost level, and it goes down. Second time, it will not attain the exactly same level, little bit less than the previous one. Why? Because of the gravitational force, right? Because it tries to come to the equilibrium position. So that's why the first time the motion will be at the extreme level, maximum height. Function is increasing. Just think like this, function is increasing. After attaining the maximum height, it starts decreasing. Calc 1, application of derivative. Whenever function is increasing and start decreasing, means increasing nature converts to the decreasing, reverse direction. What does it call? It is called critical number. Critical number. Am I right? That means whatever solution I'm going to get over here for this problem, I'm going to get I will be taking the derivative and I will equate that derivative to 0, because that's what the process says to find the critical number. So take the derivative and equate that derivative to 0 to find the critical number. And that will give you, at that time, it will give you find the time. Whatever the number we are going to get, that is t, use that t in your equation to find the extreme displacement, extreme height from the equilibrium position. Last part, Nina.
What is the position at the mass at which, what is the position of the
Plug that value in your equation of motion. That will provide you the position of mass at this instant, right? At this instant. Okay, Alex, read this example.
Yes, sir.
And all of you, please pay attention.
All right. A mass weighing 4 pounds is attached to a spring whose constant is 2 pounds a foot. The medium offers a dampening force of numerically equal to the instantaneous velocity. The mass is initially released from a point 1 foot above the equilibrium position with a downward velocity of 8 feet a second. Determine the time at which the mass passes through the equilibrium position. Find the time at which the mass attains its extreme displacement from the equilibrium position. This is the position of the mass at this instant.
Good. So I hope all you guys at least got the question, right, guys? Then explain the same thing 2-3 times. Now let's start the solution. I think now the solution is not that hard because now everything, you know the thing, so everything is good. Example 7, look at here. Beta equal to 1 as I explained to you, x0 equal to -1 foot, x at 0 equal to 8 feet per second, w is equal to mg, k spring constant is 2 feet per lb, provided to you. I found my m equal to 1/8 slug. plug these values in my equation of motion. Getting coefficient 1 means to get the coefficient 1, I have to multiply throughout by 8. That's what I did here. And then after I just went over here just to compare this one with my 2 lambda equal to 8 and the omega square equal to 16. So lambda equal to 4, lambda square minus omega square. In this case also it is 0. So critical damping, you will not get every time critical damping, right? It depends. And then after I solve this quadratic equation, I wrote it down the auxiliary solution. Auxiliary solution is in this form. -4 and 4 roots are real and same, real and repeated. That means article 4.3 says that xct or xt, because right hand side is 0, complementary function itself will work as a general solutions of c1 e to the power or c1t or whatever you want to write, c1t e to the power -40 and c2 e to the power -40. Use the first initial condition x at 0 equal to -1. So that will provide you the first constant C2. Then after, second initial condition requires the derivative. So go for the derivative of the last equation. It's a product rule over here. So I took derivative. I have 3 expressions over here. I use the second initial condition. I'm getting my second constant C1 equal to 4. Let me go back and plug this value over here for C1 equal to 4. C1 equal to 4. That means I'm getting xt equal to C1 equal to 40 to the power -40 and negative e to the power 40. So from here, I'm moving like this. Now, clearly I mentioned this thing, my answer of the question 1. So question 1, what will happen? Look at here, question 1 was, yes please, what was my question 1? xt equal to, yes, when time will come when it will be, I'm getting the equilibrium position. So let me this xt, whatever the solution I'm getting over here, particular solution, because we have the particular values of two constants C1 and C2. So if I plug it over here, if I equate this one to 0 and solve for t, see here, e to the power -40 out, 40 minus 1 equal to 0. Exponential function never be 0, 0 product rule. That means 40 minus 1 equal to 0, so t equal to 1/4 second. So after 1/4 second, once you hang the release it, after 1/4 second, system or spring mass system will come to the equilibrium position, 1/4 second. These all are the practical examples, so you have to mention the unit. If you don't mention the unit, means you are losing your points. My first answer is over. Second answer, as I told you, second answer, that means we are looking for the maximum displacement, extreme displacement. Means it's a first derivative. We are going to find the critical number. Means first derivative equate to 0. Let me take the derivative of this solution. If you take the derivative of the solution, again it's a product rule over here. So product rule over here, and derivative of the last part is this one, 4 e to the power -40. And if you equate this derivative, if you solve this 4 e to the power -4, and 4 is 8, and this is -16, and if you equate to 0. If you equate to 0, this one you can solve for t. So t equal to ½ second. So at ½ second, it will be, see at 1/4 second, this is the spring mass system. I put the weight over here and I just release it. I release it. That means at 1/4 second, it goes to the equilibrium position, and another 1/4 second, it will go to the maximum displacement. And that makes sense, right? Because from here to here, it requires less time, and here to here, it requires a little bit more time than the equilibrium position. So here I'm getting t equal to 1/2 second. So that makes perfect sense. And that is the answer of my answer of my second part, second question. T equal to 1/2 second, the spring system will attain the maximum displacement. What is the position at this time? Just plug t equal to 1/2 in my general solution xt. So xt equal to, see what is the value? So x at ½ equal to, replace t by 1/2, t by 1/2. So 1 over e to the power 2, that is equal to 0.135 feet, will be the answer of the third question. Any doubt here, guys? Any doubt here? You want some time to go over this one? Up to here, I think first part is okay, very easy. Just you need to pay attention on last 3 questions. I give you 2 minutes again. Go ahead. Okay, guys. So next one is example number 8 and number 3 from the practice test. I think that is same. You can do it yourself. I don't want to go through everything, but solution is already there with you. And now I would like to go over example number 8 and 9 also. I think, let me double check. Yeah, example number 9 is slightly different. Slightly different. What I'm going to do, let me read first example number 9. Example 9. Who? Let me find somebody. Will Hostetler. Read the example. Slowly. Slowly. I know.
You ready? Good.
Go
All
ahead.
right. A mass weighing 16 pounds stretches a spring. What is that?
8 by 3 feet.
8/3 of a foot. The mass is initially released from a point 2 feet below the equilibrium position, and the subsequent motion takes place in a medium that offers a damping force that is numerically equal to 1/2 the instantaneous velocity. Find the equation of motion if the mass is driven by an external force equal to F of t equals 10 cosine 3t.
Right. Would you like to explain to me the first 3 lines? A mass weighing 16 pounds means W equal to mg, m equal to W over g, 16 divided by 32, 1 by 2 slug. Like this. Go ahead.
Well, didn't you just explain it?
I want you to explain.
Well, you got to convert the mass to slugs. So you divide it by 32.2 pounds per second squared.
Not 32.2 is 32. 16 divided by 32. Means
Well,
it is 1 by.
gravity in the English system is 32.2.
No, I did not. G is gravitational force is always 32 feet per second square. It's not 32.2. It's 32 always.
It's 32.2.
Okay, go ahead. Go ahead.
Okay.
Next.
All right. And then, so it gives you the spring constant. So, okay. Well, you can find the spring constant through that. So, I believe it's.
Hooke's law.
Oh, yeah.
What
I
is
think
Hooke's law? Yeah, go ahead. F equal to Kx.
F equals to Kx. So,
right? And the spring, the stretch is the spring 8 by 3 feet. Means X is given to you 8 by 3. F, what is your F?
your F would be the 16 over 32, correct, which is 1/2.
So no, not 16 over 32. That is M. F is simply 16.
Okay.
So F equal to Kx, F is 16. K you are looking for, X equal to 8 by 3. Naturally, you can find the spring constant. Agree?
Yes.
Next.
Okay. And then it's released from 0.2 feet below the equilibrium position. So
Wait. Yes.
Yeah. Yeah. So that would mean it's the spring constant times that is the initial force that's applied to it.
No. What does it mean? 2 feet below the equilibrium position means X at 0 equal to 2 feet. Agree? Initially means when time t equal to 0. So X at 0 equal to 2 feet. Does it make sense, Will?
Yes, since it's already stretched from the.
Now the stretching part, everything is done. Now right now we are setting up the initial conditions.
Mm-hmm.
The mass is initially released from a 0.2 feet, right? From a 2.2 feet initially released. The mass means once you pull the mass, that is 0.2 feet. Now release it, right? So initial condition that is 2 feet.
Mm-hmm.
And yes, equilibrium.
After that,
subsequent motion takes place in the medium. Okay, go ahead.
Yeah, then after that, it gives you the damping force, which is beta equals to dx over dt, which equals 1/2 dx over dt. So that means
your beta is?
Beta would be 1/2.
Correct. Then?
And then find the equation of
the equation of motion. Yep. Go ahead.
Yes, and then find the equation of motion if mass driven by an external force equal to f of t equals 10 cosine 3t. So then,
Yes,
yeah, this
I
is
have
the
not.
part.
I
Yeah,
didn't. I have not taught you so far. Just wait.
yeah, I was about to say.
I have not taught you. I can't ask you.
I
Good efforts. Okay, guys, look at here now. Find the equation of motion if the mass is driven by an external force equal to Ft equal to external force. In my first part, it was just free motion without damping. In second part, I had damping force, but no external force. Now I am applying, damping is already there, but I am applying, externally I am applying some force to my, like this. I'm just applying some force to my mass. If you apply some force, that means your right hand side is now 10 cosine 3t. Right hand side is not 0 now. That means you are not simply finding your xc. Will here, please. Will, please. No talk.
Yeah.
So you are not simply finding your xc. You are finding your p, particular integral. Then we are going to add sum of both of these things to get my general solution, and then I will proceed further. Are you getting me, guys? So here right hand side is non-zero. This is the practical example of undetermined coefficient, article 4.4 of your previous chapter. Does it make sense? Oh my God. Say yes.
Yes, sir.
Right. Paul, are you okay?
Yes, sir.
Good. Let's go through this solution, guys. It's simple. Already I give it to you. It will be a little bit lengthy example, but that's fine. Example 9. Look at here. W equal to, now will, whatever you spoke, we have exactly the same thing, 1/2 slug, S equal to 8/3 feet, right? So Hooke's law says that 16K as 8/3K equal to 6 feet per LB per feet. Beta equal to 1/2 as you explained to us. Initial condition X at 0 equal to 2 feet. Velocity is not given, means it is 0. Always we assume like this. Equation of motion with damping. So m d square x by dt square plus beta dx by dt plus kx equal to f of t, because f of t is given to you now, right hand side non-zero. Divide by m throughout. If I divide by m, after dividing by m, I can go for this damping nature. So just plug the values and then divide by m. So multiply throughout by 2, so that I'm having the coefficient 1. So this is my damping, and this is my right hand side. So this is my 2 lambda. You can see here my 2 lambda is nothing but beta by m. You can say this one, or you can say 1 here. I don't mind. And my omega square is 12. K by m is 12. Plug this value over here. I did not explain to you, but you need to write this one. Yeah, here it is. Here it is. So plug these values, and you can see here you are going to get plus or minus square root of 47/2i. Means it's a, this is less than 0. Omega lambda square minus omega square is less than 0, means it is under damping. So you need to mention, you have to mention this thing like this. Then after again go back to your auxiliary equation. Find the value of m's quadratic equation solution. You are going to get negative 1/2 plus or minus root 47/2i. Complex conjugate roots. Article 4.3 says that, all of you pay attention here. Article 4.3 says that complex conjugate root means e to the power alpha x, c1 cosine beta x, c2 sine beta x. So alpha is, it's actually t here. Alpha equal to negative 1/2 e to the power alpha x, alpha t. So alpha is negative 1/2 t. C1 cosine beta t, C2 sine beta t, because t is your independent variable. Now, this is my xc. You have to specifically mention this thing. But what is my right hand side? My right hand side is 20 cosine 3t. Don't say 10. It has to be a coefficient 1 here. So 20 cosine 3t. So because cosine is there, that means I can assume my xpt equal to a cosine 3t plus b sine 3t. A cosine 3t plus b sine 3t, right? Article 4.4, formula sheet for your assumptions. Whenever trig function is there on your right side, always we assume sine and cosine, right? If it trig sine or cosine is there, we assume both sine and cosine. So a cosine 3t, b sine 3t. check your glitch. There is no glitch here because here it is exponential. There is no exponential here. So I'm good out of glitch. Highest derivative is 2. Let me go for, you need to mention this thing. I forgot, but you need to mention that no glitch. In exam, couple guys, they just memorize the answer. Yeah, let me just stop over here. And let me just talk a little bit about your exam. Couple guys, 2 guys, yes. That one of the examples that was EX and something like that, directly they mention EX squared. Just they memorize the things. Don't do this thing. If you are trying to memorize the examples next time onwards, in the last exam as well as the final, I will change all the numerical data. I'm helping you. That doesn't mean that you can misuse the liberty, misuse whatever I'm providing to you. Please don't do this thing. Don't try to memorize the example. Please work hard, try to understand the things. Math is not to be memorized. No, math is to be understood. Okay, let me come to my problem. The xp dash and xp double dash second derivative is their highest derivative. I took the derivative. I plug all these 3 values over here in my equation. In my equation here, look at my cursor. If I plug these values over here, then I'm getting this equation. Let me consider the coefficients. Sine t and cosine t coefficient. Cosine 3t here. Cosine 3t here. Look at here. I use same lines for my cosine 3t and different just write symbols for sine 3t. And I use the coefficient. I collected all my coefficients. Cosine 3t, sine 3t, and right side is just cosine 3t. Sorry, cosine 3t. If you compare the coefficient, you're going to get 3a plus 3b equal to 20, 3 minus 3b equal to 0. You can go for RREF matrix, but it's just 2 variables. So I think 2 constants. It's not a big deal. So if you solve these 2 equations, you are going to get a equal to 10 by 3 and b equal to 10 by 3. Go back and plug this value of 10 by 3, 10 by 3 without glitch part. Of course, no glitch was there. So just 10 by 3, 10 by 3. Take 10 by 3 out, cosine 3t plus sine 3t. That would be your xt. That would be your xt. So xct plus xpt, that is my xt. X is this one and xp is 10 by 3 cosine 3t. This is now my general solution. Now I'm going to use my initial conditions, whatever I had over here. I'm going to use these initial conditions to find the final answer. So now I'm going to use that initial condition. Look at here, guys. Now the initial condition, xt. This is my final general solution. My first initial condition, x at 0 equal to 2. It's a long example. Whenever right hand side is not 0, it's always a long example. So please keep in mind this thing. So x at 0 equal to 2. Plug it back over here, replace t by 0. Means your left side is 2. T by 0, cosine 0 is 1. So you're going to get e to the power 0 is 1. So c1 plus 10 by 3. So c1 plus, yeah, that is equal to 2. So c1 is negative 4 by 3. Just go back and plug it over here. So first initial condition gives us the value of my first constant. Second initial condition, as you know, that contains the derivative. You have to take the derivative of such a big expression. You don't have any other choice, guys. You have to. I'm sorry, but you have to. So x dash t equal to negative 1 by 2, negative 1 by 2 e to the power negative 2 by 2, negative 4 by 3 cosine square of 47 by 2t, and this one. What I did over here, it's a product rule here. So e to the power, I took the derivative of this one, e to the power negative t by 2, and derivative of negative t by 2 is negative 1 by 2. And this part as it is. This is as it is. Now, e to the power negative t by 2 as it is, and derivative of cosine is, this constant term. Cosine is negative sign, so negative is positive, and chain rule. Sine of mt, cosine mt is negative sine mt times m, and same here, right? So chain rule. And finally, cosine 3t is negative 3 sine 3t, sine 3t is 3 cosine 3t, derivative. And such a big expression. One single mistake will make all the whole example wrong. So please be careful, don't get tired. And now I'm allowed to use my second initial condition, velocity condition over here. If you use the velocity condition, my left hand side is equal to 0. Replace all t by zeros. That means I'm getting like this. And that will provide me the second condition, second constant, sorry, C2. And C2 equal to negative 60 for what it may be. Just go back and plug, see, look at my arrow. Plug back in my last solution. Here it is C2, 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 where is C2, C2 here, right? And that is my general solution. That is my general solution. Look at here, guys. That is my general solution. I wrote it down example 10 homework, but I gave you the solution too. So first try example 10 without looking at the solution. If you are done, once you are done, compare your solution with the given solution. If everything is good, you're fine. Otherwise, try to figure it out your mistake. Try to solve your mistake. But solution is already there. Look at here. This example is almost same. Here it is, instead of cosine 10 cosine 3t, it is 8 sine 4t. That's the only difference. Other things are almost same. So example 10 is just similar to my previous example. Any doubt? Any doubt? I'm asking you guys. I'm talking to you. I'm not talking to anybody else.
No.
Thank you. Girls, are you good?
Yes, sir.
Okay, both of them. Where is Margie? She's here. Margie, are you okay?
Mhm.
Nina?
Yes, sir. I'm good.
Okay. Nick, are you good? Nick Campbell?
No doubt, sir.
Good. I think heart is good. Hey, my friend Levine, smiling face.
Sir.
Good.
Sir.
Good. If you have, see, I can't speak all the names every time. All you guys are equal for me. So if you have any doubt, you can stop me at the same time. Don't hesitate, please. Don't hesitate. Okay, anytime you can stop me. Okay, example number 11. So now my article 5.1.1, 5.1.2, 5.1.3 from your book, these three articles are over, and I would like to switch over to electrical network circuit for second order differential equation. First order differential equation, I used that one in chapter 3. Now it is chapter 5, electrical network circuit. Okay, guys, again, you need to draw the picture like this. You have to mention everything. You have to put this small arrow so that we can come to know that current passes through different component of the circuit, right? These are the things provided to you in the example, and we are looking for the current passing. What is the current from the circuit? But here it is not current, but actually it is Coulomb, Q. I told you, if you remember in chapter 3 application, that whenever capacitor is there, and if you're looking for the not I, but Q, at that time, you are working with second order differential equation. In chapter 1, we converted our Q to I, but now we are converting I to Q, and capacitor is there. So Kirchhoff's first law says that I1, here first law is I1 equal to I2 plus I3, but we don't have any others, just one loop circuit, one closed loop circuit. All of you here, please. I said all of you here. One closed loop.
Yes, sir.
Yeah. So current passes through the inductance L is given by L into di by dt. Can you see my cursor? Current passes through capacitor is given by Q by C always. Q by C. You know this thing. We did this thing in chapter 3 also. Only thing is we are solving now for Coulomb, Q. That's the only difference. Otherwise it is exactly same. Current passes through resistance is given by R times I. And then current goes to the circuit.
He said you could get the same kind of watch that he has, which
I can't hear you. Say again. I'm sorry, guys. I can't hear you. Who was there? Ilyas? Somebody's. Who was there? Nathan? Are you okay?
Wasn't me.
Background
Yeah, it was
noise
not-
from Alex.
Alex? Where is he?
yes, sir.
Yeah. Did you raise any question?
No, sir.
Okay. May I continue?
Yes, sir.
Continue. Okay, guys. So L into di by dt. Current passes through inductance, capacitor, and resistance that is given by this one. And you know this relation between current and the Coulomb, that is rate of change of Coulomb with respect to time, that is nothing but the current. So I equal to dq by dt. I would like to convert this I to dq by dt. So now it is converted to second order differential equation d square q by dt square. And this I also, it is I equal to dq by dt. So I equal to dq by dt. Because this is dq by derivative, first order, so I just wrote it down here just to make my equation more in the more easier form. Second order, first order, zero order, descending order, right? Solomon Harris. Okay.
Yes, sir.
And that is equal to ET. Then after I divide by L, I don't plug the values right now. Let me divide by L. So R by L and 1 over LC and Q, that is equal to ET divided by L, right? And you are given what? The initial condition, Q at 0 equal to Q0, some Q0, some number, and Q dash at 0 equal to, or current I0 equal to 0. Current at I, but I0 equal to 0 is given to you. But I0 equal to 0 means it is to be understood that it is given dq over dt at 0, means Q dash 0 equal to 0. So these two are initial conditions. Okay, fine. Now, again, damping force is there. R by L is a damping force over here. Look at here, guys. Compare your equation with our general equation of motion, spring mass system. This is my damping force. This is my omega square. Omega square. So if you compare over here, 2 lambda equal to, if you want to plug the values, that's fine. Okay, plug the values here. Once you have coefficient 1, then you can plug the values. R over L, R is 10, L is 0.25 in the circuit. Look at here. Look at here. Here. And my L into C is this 1.001, 0.25 in Q. So if you simplify this one, here it is 40, here it is 4,000. So 2 lambda equal to 40, so lambda equal to 20, and omega square is 4,000. So if you take this one, you're going to get negative sign because naturally 40 square is 1600 minus 4,000. So it's a negative number inside the square root sign. So roots are complex conjugate of each other. So naturally it's under damping. So you have to mention this thing, please guys. You have to mention this thing. So it's under damping situation. Now let's go back to the quadratic equation. Solution is like this, b square minus 4ac divided by 2a, and you are getting alpha plus or minus I beta. Roots are complex conjugate of each other, type 3, particle 4.3, type 3. So qt equal to qc of t. My right hand side is 0, so qc, complementary function itself, will work as a general solution, but make sure my q is the dependent variable, so it is in terms of q of t. So e to the power negative 20t alpha e to the power alpha t c1 cosine bt plus c2 sine bt. Okay, guys. Now, my first condition q at 0 equal to q0. So c1 is q0. Second condition requires derivative. So take the derivative after plugging c1. Take the derivative of this part. Again, it's a big expression because of this product rule. You have this big expression. Once you have this expression, then, oh, sorry, my bad. Then after, I can plug my second condition, q dash at 0 equal to 0. Q dash equal to 0 equal to C, you're getting C2 equal to Q0 by 3. Go back and plug this value of C2 over here to get my general solution, and that's it. Simple. Is it okay, guys?
Yes, sir.
Yes, sir.
Some time to understand this problem? Okay, let me give you some time. I think up to here it is okay, but let me start from the beginning. I can give you 2 minutes. Go ahead. Almost time. Are you good?
Yes, sir.
Okay, guys. Sounds good to me too. Shall we go ahead, guys? Girls? Shall we go ahead, guys?
Yes, sir.
Thank you. Okay. Example number 13. Would you like to look at the problem? It's just based on the problem, I just drew the circuit. That's it. Look at here. Okay, let me just show it to you. This is problem 11. Just now we solved this one. LCR circuit. Problem 12 is similar to problem 11, so I don't want to do this thing. Exactly same. Look at over here. I at 0 equal to 0 ampere is given to you. It's same thing. Even 13 is same. Find the charge QT on the capacitor. I'm sorry. Excuse me. Sorry, guys. Find the charge QT on the capacitor in LCR circuit, series circuit, of course. L equal to 1 by 4 Henry, R equal to 20 ohm resistance, C equal to 1 by 300 Faraday. Electromotive force is 0, ET equal to 0 volt. First condition, Q at 0 equal to 4 Coulomb actually, and I at 0, I means dq by dt, that is equal to 0 ampere. Is the charge on the capacitor ever equal to 0? Is the charge on the capacitor ever equal to 0? That's the condition. That's the thing. Okay, let's start. '11 we solved, and now 13, I think so. Yeah, 12 is just similar. Okay, so I just plugged all these values over here. Again, guys, this is my fault, but don't repeat my fault. I have to mention, I have to put one arrow over here, and I have to say I, current I, right? Q at 0 equal to 4 Coulomb given to you. I at 0 equal to 0. I means dq by dt means Q dash equal to 0. L current passes through inductance is L di by dt. Ri, C means Q divided by C equal to E. Replace your I by dq over dt. So dq over dt, second order differential equation. Please convert to dq over dt. Don't convert everything in terms of I, please. I request you. Right? Otherwise, it will be simply, but I think you can't. Yeah, because if you write dq by, if you take the derivative over here, suppose you want to convert to I in this problem. Suppose here I converted everything in terms of Q, right? But suppose I want to convert to I. Somebody says that, no, I want to convert to I. That's fine. You can do that thing. Again, you will be ended up with the second order differential equation. See here, for I have to convert this one to I. If I want to convert to I, that means I have to take the derivative of this part. Derivative of this part, you can't take it. You have to take the derivative throughout. So if I take the derivative here, d square I by dt square, r di by dt, and dq by dt is my I. See? So same as this equation, q is replaced by I. Just simply that part is there. That's why I told you that whenever capacitor is there, you have to be very careful. You are working with the higher order differential equation because of the capacitor. Same thing, auxiliary equation. Again, my fault. I did not mention over here my damping, but did I? Oh yeah, it's just writing down one line over damping because my M is positive and different. So real numbers, real distinct numbers, if you take 2 lambda and omega square, lambda square minus omega square will give you greater than 0. And that's why it is real and distinct and over damping. But please show your work, please, please, please. This is just the second time repetition for me, and that's why I did not write everything, but I just write down directly. You don't write directly, please. You have to show it to me. So QT is this one. My first initial condition is this one. Quite simple, guys. And then after, First condition will give me the value of C1. Second condition, look at over here, will give the value of C2, value of C2. And finally, answer is, will it pass to the equilibrium position? For equilibrium position, that means whatever x I have, right? So just equate to 0, right? And you will come to know this thing. Look at here. So this is my solution. Okay, guys, this is my solution. So qt equal to 6 e to the power negative 20t minus 2 e to the power negative 60t. That is the solution. That is the solution. All right, what time, if you want, if you're looking for time, you can equate this one to 0 and try to figure it out your time. So here e to the power negative 20t is common and 6, and here it is t, what it may be. So this way you can find the time if it is asked to you. Again, the same similar kind of examples. So I don't want to go through the same examples again and again. Just do it. And if you have some doubt, you can ask me. So I think this is all about your article, or I would say chapter 5, application of higher order differential equation, spring mass system and LCR circuit. Would you like me to start the new chapter today or tomorrow? I'm asking you guys.
I vote tomorrow, sir.
Zeal is always there. Anyway, guys, that's fine. I can understand. Yeah, you need to go through all these things. So that's fine. No problem. I'll see you tomorrow. Try to go through this one. If you have some doubt, just now, I mean, say Friday, you finished your exam. So today, there is no point of discussion of anything, because usually, as we have decided, we are spending 10-15 minutes for your doubts, your discussion. Even though if you want to discuss something, go ahead. Otherwise, we can stop over here.
Sir, real quick, so you said test 4 is on Wednesday, since you're gonna have to cover Laplace transformation at the beginning of the week?
No,
Next week?
not this Wednesday. It is following Wednesday.
Well, yeah, like next Wednesday instead of this Friday?
Yes, that's what I'm thinking. But because your exam, you are going to take your exam on not Friday, following Friday, right?
Yeah.
I believe so.
Final exam. Yeah. So that's why I want you to take your exam. I was just would like to give you some more time. That's it. But I'm not sure. Right now we have. Let me just stop this and.